In my last video, we looked at precision rectifier circuits using dual supply op amps. However, in a lot of cases, you may need to have a single supply rectifier. So today we're going to take a look at some single supply op amp rectifier circuits and talk about some of the inherent limitations to single supply operation and look at some ways that we can improve single supply performance even beyond that of their dual supply counterparts. So let's start by taking a look at a simple single supply half-wave rectifier circuit. And this can be nothing more than a simple unity gain inverting op amp. And this relies on the fact that the op amp can't drive its output below ground, since ground is its negative voltage supply. So when we have some input that's centered around 0 volts, since this is an inverting configuration, when this goes positive, the output is going to try and drive negative, but of course it's just going to be clamped at 0 volts. And then when the input goes negative, this will invert it and we'll get our positive half of the output here. So we've now half-wave rectified this by simply clamping the output of the op amp to ground. Now there are a couple things to consider here. First of all, ideally you want an op amp that is rail to rail and can drive its output all the way down to 0 volts. The other thing to consider is that even with a rail-to-rail op amp, when you drive this op amp's output all the way down to 0 volts, you're going to be saturating the op amp, and it's going to take some time for it to come out of saturation once it tries to output a positive voltage here. And at lower input frequencies, and that's usually not too big of a problem, but as you increase the frequency of your input signal, that can start causing distortion on your rectified waveform. So let's head on over to the bench and see what that looks like. Now I have a microchip MCP601 op amp hooked up on the bench in an inverting configuration. And this op amp is a rail-to-rail op amp, and its output does include 0 volts, so it can go all the way down to the 0 volt rail. And with a fairly low frequency input of 100 Hertz, we can see that the output in green looks pretty nice. It's a nice rectified circuit. It seems to be tracking the input very well, and there's no visible distortion on the rectified output. However, if I increase the frequency here to, say, a kilohertz or so, if you look closely, you can just start to see a little bit of delay in the output of that rectified signal. So there's just a tiny little bit there that you can just see where it's kind of jumping up to meet and track the input waveform. And this will just get worse as we increase the frequency. If we go up to, say, 10 kilohertz, you can see that has gotten much worse there. And if we go up to, say, the top of the audio range, 20 kilohertz, it gets significantly worse. So you can clearly see that there is a delay in the output because that op amp has to bring itself out of saturation, and it takes some finite amount of time to do that. Now, if we want full wave rectification, all we have to do is take that same circuit and add a diode. On a positive going input signal, the op amp is going to invert that and try and drive its output negative, so it's just going to drive down to 0 volts. And that's going to reverse bias this diode. So effectively the diode is not there and the op amp is taken out of the feedback loop. So our input signal arrives at the output through these two resistors. So we get a nice little positive hump here from the positive input portion of the signal. On a negative going portion of the signal, the op amp is going to invert that and it's going to start driving its output positive. And so that's going to forward bias the diode. The op amp is now in control of the feedback loop, and it's simply going to track the negative going input signal, except it's going to invert it. And so we get a nice little positive hump here, and we've now full wave rectified that input signal. And if you watched my previous video on split supply full wave rectifiers, this circuit should look familiar to you. In fact, it's the very first full wave rectifier circuit that we discussed in that video. And it has all of the same limitations here that we discussed in the previous video. So for example, the output not only has to come out of saturation when it tries to drive its output high, but it also has to shoot up fast enough to forward bias this diode quickly enough so that we don't have any noticeable distortion here. So that's going to add some frequency limitations to what frequencies we can handle without distorting our output, because op amps have a finite slew rate, unfortunately. We've also reduced our dynamic range by about 600 millivolts because we need that 600 millivolts to forward bias this diode. So with a rail-to-rail op amp, they typically can go really close to their voltage rails within, a couple of millivolts in a lot of cases. But we've lowered that dynamic range, the peak voltage that we can handle, by 600 millivolts in this case. So at lower frequencies, this works very well. You can see that we have a nice fully rectified output waveform here, and there's no visible distortion at all. However, if we crank the frequency up, we're at 100 hertz, we'll bring it up to something much larger, like 20 kilohertz here. You can see that there is a significant amount of distortion on the output now. And if I switch channel 1 here over to the output pin of the op amp, we can see why. This here is the zero crossing point, and this is where the op amp's output should start driving high in order to forward bias that diode, but it doesn't actually come out of saturation until about right here. And even then, it still needs to forward bias the diode, and it has a limited slew rate, so it takes some finite amount of time to do that. And so that's where this distortion is coming from, because our op amp is not coming out of saturation immediately, and it takes some additional amount of time to forward bias the diode. But you'll notice that the majority of this delay is actually in coming out of saturation, not the forward biasing of the diode. This period here is larger than this one. So the major limitation here is not necessarily the forward biasing of the diode, because we could get a diode that has a lower forward voltage, like a Schottky or a germanium diode. But the majority of the delay here is actually in the op amp coming out of saturation, and changing the diode is not going to help that. Now, as viewer Tech Constantine pointed out, you can actually do the exact same thing by replacing the diode with a resistor. And you'll notice the resistors now have very specific unequal values. And that's because you need that if you want to have a uniform full wave rectified output. So with an input signal that's going positive, the op amp again tries to invert that and drives its output to 0 volts. So what we have here is the input signal that's positive going connected to our output point here through a voltage divider of 30 kiloohms and 30 kiloohms, because this point is really a virtual ground at this point. And so what you get is the positive going half of the input signal shows up on the output, but attenuated by 1/2. Now when the input drives negative, the op amp's going to invert that and start outputting a positive voltage. And from the standpoint of our output of the circuit here, we see that we have two feedback resistors here, 10K and 20K, which is going to give us a gain of 1/2. So again, we see half of the amplitude of the input circuit, but it's been flipped around so it's rectified, and we get a nice full wave rectification. However, in order to accomplish that, the op amp actually has to output twice the input voltage on its output pin. So if we look at what the op amp sees here and on its output, it has 30K in series with 10K connected back to its inverting inputs. That's 40K, and then you have a 20K input resistor here. So that's actually a gain of 2 as far as the op amp's concerned. So even though we only get half the amplitude out here, the op amp's output has to drive to twice the input amplitude. And so we've now lowered our dynamic range to 1/2 of our supply voltage, because the op amp's output has to drive to twice the input voltage. So our output is reduced by 1/2, and our dynamic range is reduced by 1/2, and we still have issues with the op amp going into saturation and the distortion caused by the delays in coming out of saturation. However, it does get rid of a diode and replaces it with a resistor, and that can be quite useful in certain situations, especially if you already have a bunch of resistors in your bill of materials. It can actually be quite a bit cheaper to just slap another resistor in there rather than adding a diode. So again, we can see that this works really well at lower frequencies. We have nice, clean, undistorted, rectified output here at 100 Hertz. Although, as you'll notice, it is 1/2 of the input amplitude, but that's exactly what we expected. And of course, if we roll this up to higher frequencies, it's going to start getting a lot more distorted, just like we saw in the previous circuit. So you still have distortion, but it is a quite clever little circuit that saves you a diode. Now, while there's certainly something to be said for simplicity, if we want to improve the functionality of our full-wave rectifier, it typically requires the addition of some extra circuitry. Now, this is a clever little circuit that actually addresses several of the issues we've seen so far. The first thing you'll notice is that there's no resistor or diode here at the op-amp output, which means we are maximizing our dynamic range because we're not going to be losing a voltage drop here across a resistor or a diode. So without the diode in place, the way this circuit full-wave rectifies an input signal is it uses this portion of the circuit to switch this op-amp between an inverting and non-inverting unity gain configuration. So let's consider what happens with a positive going input signal. When this signal goes positive, it's going to show up here at the positive input of this op-amp and at the negative input of this other op-amp. Now when this inverting op-amp sees a positive voltage, it's going to drive its output down to its negative rail, which is ground, of course, and that's going to reverse bias this diode. So effectively, this is really doing nothing in the circuit at that point, which leaves us with this configuration, which is simply a unity gain non-inverting amplifier. Now, it might not look like your typical unity gain non-inverting amplifier, so if you haven't seen this configuration before, it's actually pretty straightforward. If we consider that we have an input voltage source here, and the op-amp itself is a voltage source, we can build a little circuit to model this and calculate the Thevenin equivalent voltages. So let's say for simplicity that our input voltage here is just a DC voltage of 1 volt. Now to do a Thevenin equivalent, we take all of the other voltage sources and short circuit them and just pretend that they're not there. And when we do that, we see that we simply have 1 volt applied to a voltage divider that's going to knock this down to 1/2 volt. Now since this point is connected to the inverting input of the op-amp, and we know that the input voltage is also going to be applied to the positive input of the op-amp through this 10K resistor. We know that this point is going to be 1 volt, and so the op-amp is going to want to drive its output so that this point is also 1 volt. Now we already know that there's a 1/2 volt applied to this point by the input voltage here, so the op-amp has to output a voltage that adds another 1/2 volt to this point in the circuit, and the only way for it to do that is to output 1 volt, which is exactly what our input voltage is. So again, do the Thevenin equivalent where we now short out this portion of the circuit, and again we just have a voltage divider, 1 volt applied to two 10K ohm resistors, which gives us another 1/2 volt. So the op-amp in fact will drive its output to be the same as the input voltage. So this is a unity gain non-inverting configuration. Now the major advantage to using this particular configuration for a unity gain non-inverting amplifier is that it's actually very easy to switch it into being a inverting unity gain amplifier by simply grounding the positive input. Then really all we have as far as this portion of the circuit is concerned is a simple inverting unity gain amplifier. Now there is an additional 10K ohm resistance going from the input signal to ground here, but as long as your input source impedance is fairly small, that's not going to matter at all. So this is exactly what this second op-amp and this diode do for us, because we've already seen that when the input signal is positive, this diode's reverse biased, and this is basically non-existent as far as the circuit's concerned. But when the input goes negative, this is going to flip that, of course, because it's an inverting op-amp, and it's going to forward bias this diode. It's going to start outputting some positive voltage here. Now when it forward biases this diode, it now has control of its feedback loop, and it's going to output whatever voltage it needs to hold this point at 0 volts because its positive input is tied to ground. So if this point is held at 0 volts, and that's connected to this point in the circuit here, then this point in the circuit is connected to virtual ground. And so it's effectively grounded, and this second op amp has now, for all intents and purposes, flipped this op amp to be a inverting configuration. So on positive going signals, this portion of the circuit is basically non-existent, and we have a unity gain non-inverting buffer, which gives us a positive hump on the output. And for negative input signals, this portion of the circuit flips this op amp to be a inverting configuration, so it inverts the negative input and gives us another little positive hump here, so we get this nice full wave rectified output. However, there is going to be, again, some delay in doing that because this op amp itself is going to be driven into saturation on a positive going input, because with a positive going input, he's going to reverse bias this diode. He's just going to slam his output down into the negative rail, which is ground. So you're taking the burden off of this op amp and placing it down here. But this actually works very well, and you can get a significant reduction in distortion with this particular circuit. So again, this works very well at lower frequencies. And again, if we crank this up to a higher frequency, like 20 kilohertz, we'll expect to see some distortion on that waveform. But the distortion actually doesn't look as bad as it did before, and the main reason for that is that our output from the rectifier is not going negative here. It's getting clamped at 0 volts due to the different configuration of this circuit. So there is still saturation going on here, right? Both op amps really are saturating and not turning on immediately. And we can see that if we take a look at the output of the second op amp, which is responsible for forward biasing the diode. You can see that this is the zero crossing where it should start going high, but it takes some time for it to come out of saturation and forward bias that diode. But even once it does, the first op amp is also saturated, and so it takes some time to come out of saturation as well. So there is still saturation going on here. There are still delays, but because the output doesn't go negative, the waveform looks much nicer, and when this first op amp does come back on, it has a shorter distance that it needs to drive its output before it starts tracking the input again. So instead of having to drive from, say, down here up to here, it only has to drive from 0 volts up to this point. So it does actually reduce distortion at higher frequencies, even though there's still saturation and delays. So we could try to combat this distortion by getting a faster, more expensive op amp, or we can redesign the circuit to work smarter instead of harder. So if we take that same concept, but instead of using another op amp to switch our amplifier between being an inverting and non-inverting state, we use a comparator and an analog switch, we can get much better performance, because this comparator is designed to be turned on and off very quickly, and it's designed to go rail to rail, so we're not going to have saturation issues there. And the FET switch works very well for shorting the positive input to this op amp to ground. Now in this particular configuration, I've added a resistor and a diode here just to protect the input of the LM393 comparator from the negative voltage swings on the input. I've also added a simple little inverter here to invert the comparator logic in order to properly drive this analog switch. And the analog switch is, pretty much a jelly bean part here. It's a 4066, so it's nothing really out of the ordinary. So when we have a positive going signal here, the comparator's output is going to go high. That, of course, will turn off this inverter, and that will turn off the switch. And so the switch is effectively disconnected from the circuit, and we have our non-inverting amplifier. When the input crosses 0 volts and goes negative, the comparator will go low. That will turn on the inverter, which will turn on the switch, and that will short circuit the positive input of this op amp to ground, and now we have our inverting configuration. So exactly the same concept as before, but in this case we're using inexpensive components in a way that they were designed to be used. So instead of using an op amp to do a comparator's job and short circuit the positive input here to ground, we're using a comparator to do the actual comparison and a FET switch in order to short circuit the positive input to ground. So with this circuit at 20 kilohertz, there's hardly any distortion visible on the rectified output. Certainly there is some. If we zoom in here, you can see there's a little bit of distortion down there towards the bottom of the waveform here, but it's really not nearly as bad as we were seeing before. So even if we rolled the frequency up to, say, 50 kilohertz here, of course the distortion does get worse, but it's not severe even up at 50 kilohertz. So even though it's using fairly inexpensive operational amplifiers, this circuit operates much better up at higher frequencies than the other circuits we've considered so far. And just in case you're wondering how this compares to a dual supply rectifier, here you go. This is the dual supply 2 op amp rectifier that we talked about in the previous video, fed with the same 20 kilohertz input signal, and we can see very noticeable distortion on the rectified output. Now this isn't terribly surprising because even though in the dual supply configuration we're not driving any of the op amps into saturation, the op amp still has to overcome the diode drop. Well, actually 2 diode drops if you recall. So if we take a look at the actual output pin of the op amp that's driving those diodes, you can see that it's going from about 0.5 volts down to about negative 0.6 volts here in order to overcome those diode drops. So there's not really much of a delay between the zero crossing and the time that op amp actually starts trying to forward bias those diodes. In fact, you can see the voltage starts dropping here from the op amp, in fact, a little bit before that zero crossing. But the major delay is actually in overcoming that forward voltage drop, and that's due to the limited slew rate of the op amp. So although this configuration has a higher component count than all of the others that we've looked at, it definitely has better performance. And if you consider the cost of using one of the previous circuits with a higher end op amp that might cost several dollars a piece in small quantities, this circuit is actually cheaper, especially if you're manufacturing in large quantities like 1,000 or more, because we're using very generic jelly bean components because we're not pushing the components to their limit, trying to make them do things they weren't really designed to do, like having an op amp act as a comparator. So although there are situations where this circuit is not going to be ideal because you might be optimizing for low power or you might need to optimize for size, so the additional circuitry here might not be desirable, you shouldn't confuse simplicity with cost or performance. So I hope you enjoyed this video. Thanks to the viewers for sharing their circuit suggestions, and if you have any interesting rectifier circuits that you'd like to share, be sure to post them in the comments below. Thanks for watching.